Hi. So this time we're going to talk about another method for propagation modeling called ray tracing. This is the oldest method, the original method, and I think people love to use it because it's quite intuitive. The basic idea is that, we've been looking at sound as plane waves. Now we can look at sound as rays propagating in the direction of propagation. And as we go from one boundary to another, C1, row 1, C2, row 2, where these changes are small, depending on the angle of the ray, we want to understand, how that ray is going to refract through these different changes. So where do we start? As always, we start with the Helmholtz equation. Start with Helmholtz. And we'll just write this in terms of pressure. Put our source with unit source strength at XS, and we're going to say in a homogeneous medium. So, as always, a good idea to do with any partial differential equation is to guess a solution. And there's some very general forms of solutions that work really well for defining all sorts of functions that end up being useful. And so you probably remember from an ODE course or PDE course, power series solutions. That's exactly what we're going to do here. So we're going to say, suppose the solution has form P of x equals e to the I omega tau of x, and then sum over j amplitudes AJs over I omega to the j. This is called the ray series solution. So first things we need to do when we employ these methods, right, is calculate the derivatives. So I will just do that. I'm just going to go straight to the second order derivative, right, because that's the one we need in our equation. If you want to convince yourself that I've made no errors, always a good idea. So we have d tau dx, I omega second order derivative of tau with respect to x, and then the sum aj over I omega j, and then we'll have a 2I omega tau x sum AJX over I omega to the j, and then we'll have one where we've just taken the sum of AJ second order derivative with respect to x over I omega j. Okay, and then we plug this back into our Helmholtz, plug this into our Helmholtz, and what do we get? Well, we need a new page for that to happen. Helmholtz becomes e to the I omega tau. Oops. Minus omega squared sum from j equals 0 to infinity of aj over I omega to the j plus 2I omega del tau, then our sum. Second term, third term. Del squared aj over I omega to the j plus omega squared over c squared. So second term in the Helmholtz equation, I omega tau sum a j I omega j equals minus the Kronecker delta x minus xs. Okay, so a little bit messy here, but just like we would with solving an ODE with a power series, we're going to do the same thing here by separating the equation now into different orders of omega. Okay. So that's going to create, an infinite number of much simpler equations. And then we can figure out which ones are important to solve. Okay. So first, let's look at order omega squared. Well, if we just isolate the order omega squared terms, we get this familiar looking equation. If we just look at the order omega terms, we get these guys here, and the order omega 1 minus, for general order omega 1 minus j, we get similar looking recursive equation here. Okay. So familiar looking, maybe from study of optics. This is the iconal equation. And these remaining equations are known as the transport equations. So it's sort of clear here that, the iconal equation is going to give us the paths of the rays, but we need to consider the transport equations to understand the energy that's transported along the rays. Okay. Now, why this is such an attractive method is that we can look at these orders, right, and say, well, what happens when omega is large? When omega is large, we only need the iconal equation to get a good solution, right? All right. A little bit vague what I mean by good solution, but essentially in the high frequency approximation, the order omega squared terms are going to be much more important than every other term in the infinite list of equations. Okay. So let's examine the iconal equation a little bit more. What exactly do we have here? Whoops. Well, C is going to be a function of x, tau is a function of x. So this is a nonlinear PDE. So we have a few methods to solve nonlinear PDEs, but the one that jumps to mind here is method of characteristics. Oops. Jumps to mind because we know we can get we can get rays that way, basically, by by assuming the solution is rays, right? Okay. So the idea is to introduce rays. Which are perpendicular to level curves. And the idea of level curves is that they're wavefronts. Of tau of x. And so what we're going to do is first of all, write the Acoustical equation in a new coordinate system, make it easier to solve. Okay, so we'll say that the ray trajectory is going to be defined in terms of s being along the ray path. Del tau is a vector perpendicular to the wavefronts. So dx ds equals c del tau, right? And so when we say dx ds squared equals c squared del tau squared, this implies that dx ds has units length. So S is the arc length along the ray. So let's just look at this equation in 1D. See how we can solve it. 1D x component. Well, we have d by ds 1 over c dx ds equals d by ds of d tau dx. Okay, that's going to be equal to second order of d tau dx ds plus d tau dx dy ds equal to c same thing. So just some nice chain rule there. And then we can factor out the d by dx's there and end up with c over 2 d by dx. Well, not factor out, reverse. Take a step backwards. Let's just say take a step backwards and get d tau dx squared d tau dy squared. So that's looking pretty good. And so we end up with a d by ds 1 over c dx ds is equal to c over 2 d by dx of 1 over c squared x. Okay. Further simplify that. 1 over c squared dc dx. Okay. Now let's take this to 3D. We would just write this as ds 1 over c. Now dx is the vector equals 1 over c squared del C. Convince yourself of that pretty straightforwardly. So really, we want to go to cylindrical coordinates now. Oops. R and Z. We're going to have dr ds equals c psi s, dz ds is going to be equal to c zeta s, d psi ds equals 1 over c squared dc dr, and d zeta ds equals minus 1 over c squared dc dz. Okay, where we've introduced some variables here such that rs zs, that's trajectory. This is the trajectory of ray, and then psi s and zeta s are auxiliary variables. And the idea now is just, I mean, these are pretty right? These equations are pretty simple ODEs, right? Very simple to solve. We can solve these numerically really quickly at many different steps and generate R and Z, and then that will give us the paths. Okay, a few more properties here, a few more things to note. The tangent of the path that's given by, right, dr ds dz ds. So the tangent vector to the ray is c psi s zeta s. Okay. This is a really nice set of easily solvable ODEs, but of course we need initial conditions. So R equals RS psi equals cos theta over C naught, right? And Z, when Z equals ZS, we're going to have zeta equals sine theta over C naught, or C at 0. Okay, where we've introduced theta as the takeoff angle of the ray. Okay, so essentially the idea here is for each ray we're going to be solving the set of equations, right? This set of equations here. And then we'll be solving them for multiple initial conditions, multiple takeoff angles. And then for each step along the ray path, we'll be doing that over and over and over again for multiple rays, and that's going to allow us to kind of give this picture of where the rays are going. So let's just write a little recipe here. so we solve for ODEs using the initial conditions. And then we're just going to repeat that to propagate the ray. So in other words, we have some vector y equals f of x y, where y is a function of r, z, psi, and zeta. By Taylor's expansion, y I plus 1 is equal to yi plus yi prime h plus yi double I, or sorry, I double prime h over 2 plus dot 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 dot. H is the step length. Along the curve. Now, so in doing this, you can look at it that way, or you can use a built-in ODE solver. So something like, Rungakutta, MATLAB, there's some ODE 45, etc. Some other things here. And for boundaries, we simply need to flag them and deal with them appropriately, right? So we know what to do with boundaries in terms of phase and amplitude by assigning them a reflection coefficient. So in the code, we just basically need to deal with boundaries as they arise. So as your ray crosses the path defined by the boundary, you deal with the boundary and then relaunch ray. Launch ray according to reflection coefficient. And that's it. That's all you really need for a good ray tracing code. And that's all we're going to cover for today. In the next one, we'll talk a little bit more about getting transmission loss and the transport equations. All right, thanks.